collection of non-intersecting geodesics. Okay. How do you construct dual tree? So take out all the lift, the complement of the lifts. You have a domains like this. Okay. And you connect them by edges. Right. This is so the distance, make the distance between this thing is 1 because our transversal measure along this geodesic was 1. Okay. So imagine all the distance between two edges is equal to 1, and you have a tree, R tree, metric tree. Okay. Then it is known that the hyperbolic metric diverges to this projective lamination lambda means the action of the surface group converge to an isometric action on this R tree. Okay? So let's apply this idea to the whole compactification of the projective structures. So because we are dealing with the surfaces, we are dealing with the convex structures in some omega, let's say, so PGL 3R. Okay. So if you have some convex structure, then you have a holonomy from a surface group into PGL3R. Okay. Then by taking index 2 or finite subgroups, you know what's the RP2? RP2 is just the identification of this two sphere by antipodal maps. And there's some strictly convex domain sitting here. Okay? And this group acts on this domain, leaving invariant. Okay? So you can lift this holonomy into, for example, SL3R by taking some finite subgroups if necessary. Okay. And SL3R is a semi-simple Lie group. It has a nice non-degenerate metric on Lie algebras. Okay. And then one can decompose this semi-simple Lie group into, for example, like take some Iwasawa decomposition, standard Iwasawa decomposition. Or using linear algebra, the image of some element gamma, this is in SL3R, you can always decompose this thing into hyperbolic part, unipotent part, and elliptic part. Okay? The matrix has this decomposition. It's a Jordan decomposition. I hope you learned this in linear algebra. Jordan decomposition. And this hyperbolic part is conjugate to our some standard this Iwasawa decomposition A part, for example, like this. A1, A2, A3, some diagonal matrix. Okay. It is known that the image of the holonomy group of strictly convex projective structure lies in all these hyperbolic isometries up to conjugation. So you can always take a Jordan decomposition like that, so that this H part belongs to this diagonal matrix. Okay. Then this guy has this one is a semi-simple integral of rank 2, and what's the image of some point in this space, AX0. Now I'm dealing with the space, not the RP2, but I'm dealing with the space that SL3 all divided by SO3. This is another symmetric space. Seemingly has nothing to do with this RP2. But anyway, if you pick some nice point in this space, the orbit of this thing becomes flat, R2. Okay? Because it has a rank 2 thing. Then using standard theory of the Lie algebra, it has a Weyl chamber, 1, 2, 3, 4, 5, 6 Weyl chambers. Okay. So imagine there's a flat. Inside the symmetric space, there is an R2 sitting inside. And this line corresponds to actually some zero set of linear function root. Okay? And fixing one Weyl chamber here corresponds to fixing some group here. If this were a hyperbolic structure, all the element is conjugate like this: lambda 1, 1 of lambda, and 0. Okay? In SL2R, you have determinant 1. So this case is a hyperbolic structure. But this direction corresponds to the sort of the center of the Weyl chamber here. Center of the Weyl chamber. So all the elements in hyperbolic structure can be conjugate like this, the matrix lying in these directions. And if you pick this point, there's a dual point here, which corresponds to the dual structure of the convex projective structures. And under this dual structure, hyperbolic structure is invariant. Okay? So there is a way to compactify teichmuller space into the convex structures and convex structures you can make sit A plus S before. So in a hyperbolic metric case, what did you do there? You associate a function. For each hyperbolic metric, you associate a function giving for each closed loop the hyperbolic length. But in this case, what you do is, it's a function going from the set of closed loops to an element in this fixed Weyl chamber. In hyperbolic structure case, this is just a real line passing through the center of the Weyl chamber. Okay? But in general, the convex projective structures, the vector can lie either here or there. So this is sort of a vector valued functions. And one can easily show this is an inclusion map. Everything is inclusion here. Okay? And then you compactify the image of this thing in here. Yeah, I need to take a projectivization actually. So if you take a projectivization of this, still it is a one-to-one map. I forgot to tell you. Say, also you take a projectivization over there, then it's still an injection. Here you can do the same thing. 몇 시까지예요? 몇 시까지라고 써 있어요? 40분? But it is less understood what are the boundary points of this compactification here. Okay? So something like you have a image here, and on the equator you have a sort of a tachymolar space, right? And there are more stuff. If you compactify it, then at the boundary here you have projective laminations. Then what are the other points here? You can just show that these points either corresponds to reducible representation or sort of a limit action on affine building. So if you take an asymptotic corner of the hyperbolic plane, you get an R3. But in this case, because this is a higher rank symmetric space, if you take an asymptotic corner of this, you get an affine building instead of the R3. Okay? So these points are either sort of a reducible representation or an action on affine building. But we want to see what it means by geometry. And it is not well understood what it actually means. And I can sort of blur the answer. For example, in this picture, so this is a point in Mumford compactification. This is nodal curve. But still, in many cases, you can give some projective structures on the complement. Okay? So even if it is degenerated, still there's some projective structures surviving. Okay? So it's a combination between these laminations and the projective structures. And I think that corresponds to, if you look at the picture, this picture in terms of sort of a geodesic current, why the compactifying thing in tachymolar space is measured lamination is obvious. And if you try to do the analogy in a convex projective case, if the area of this convex projective structure with respect to the Hilbert metric is bounded, in the limit you can always see the combination of this lamination and projective structures. For example, you see, suppose you have a sequence of projective structures here. That means you have some convex domain. Suppose it's getting larger and larger. And at the limit, this could be the whole hemisphere. Okay? In the limit, if this is the whole hemisphere, what happens? The representation space leaves invariant this equator. That means it leaves invariant lower dimensional thing, so it corresponds to reducible representation. But in this case, the area of the Finsler metric blows up. And in the limit, you do not see any lamination, curiously. But as long as the area of this Finsler metric is bounded, if you do the analogy of these Bonahans geodesic current things, you will see some part the projective lamination, and in the complement, because the area does not go to 0, neither blows up, you can always find some complement surviving, which corresponds to projective structures. So I think I confused you too much. I tend to talk about some dynamics on this hyperbolic matrix and projective structures. So you can study this thing using algebraic theory, using Patterson-Sullivan theories. And there are some questions which puzzles me. And just I will say it in words. So if you have a hyperbolic metric, you can take a unit tangent bundle. And there's a flow by geodesic flow. This turns out to be an algebraic action with respect to some Liouville measures and so on. Then there's an entropy. If you have a dynamical action, you can measure some entropy. That entropy corresponds to some geometric quantity, which is called volume entropy in this case. They are the same in hyperbolic case. But in this convex projective case, somehow I cannot exactly tell this volume entropy and some dynamical quantity, which is called some volume entropy, and some Hausdorff measures, whether they coincide or not. My guess is, except this hyperbolic case, if you deform it to become convex projective structures, then always it sort of decrease. So somehow this hyperbolic metric attains some maximal kind of entropy, and then it decreases, because geometrically you can see that if this domain is getting larger and larger, suppose you take a hyperbolic metric like this. We have a standard hyperbolic structure here, which corresponds to metric, the curvature -1. But if you think about another cone like this, you can easily show that the metric, the curvature goes to 0. So it becomes Euclidean because it becomes RP2. That means the volume entropy strictly decreases. So my guess is that the hyperbolic structure attains the maximum entropy, and then it starts to decrease. Okay. So, do you have any questions? Reducible means, so it's a representation from the surface group into SL3R. Reducible means it stabilizes some subspace in R3, except like R2 things, okay, lower dimensional things. So in this case, it stabilizes the hemisphere, so it corresponds R2. Not factor through, you can deform it from the Fuchsian one to the strictly convex. It's an open cell of R to the 16 G minus 16ths. And the Teichmüller space sit inside as R to the 6 G minus 6, and you can deform it. Then I tell you, if you deform it, then sort of volume entropy always decrease. Because in my visualization, the metric, we have to define rigorously what metric is, but it becomes flat. You can write down the equation, like what is the x squared, in three-dimensional case, kz equal -1. So in traditional case, k is equal to 1, right? So you take a sheet, hyperboloid sheet, then it's a constant curvature. But if k goes to infinity, you can show the curvature goes to 0. That means here in this picture is getting wider and wider. So at the limit, it's sort of everything are the upper hemisphere. So if you deform the Fuchsian structure, then the domain is getting larger and larger, and at the limit, you obtain a reducible representation, and sort of the matrix becomes flat. But then R2 has a volume entropy 0, right? But I'm not sure whether there is a limit. Maybe the volume entropy does not go to 0. Maybe there is some lower bound. But so this is I started off with some definitions, and I ended up with some confusing remarks.
I'm from the nonlinear dynamics, and with you mentioned some of the entropies,
right?
Liouville dynamics,
yes.
and that kind of thing. For example, some nonlinear dynamics, the phase volume decreases,
mm-hmm.
and the dimension becomes fractalized.
Mm-hmm.
So you can have the strange attractors. Then is if that space is just really strange, you don't have some continuity in certain direction, but you have something
right.
like a continuity in other directions. So then you can define some similar kind of entropy in terms of this geometry.
For example, if you have some Fuchsian space, hyperbolic structure, you can deform in PSL2C, some three-dimensional thing. Then it becomes quasi-Fuchsian. Then if you look at some limit sets, I haven't defined, but then it's a fractal image. Then volume entropy increase, actually. Volume entropy strictly increase. The minimum is attained only for Fuchsian case. And all these curves is fractal image. Hausdorff dimension is strictly larger than 1. So maybe, I'm not sure it's an answer to your question, but I hope it helps you. Yeah, yeah. Okay, so I'll count. Thank you.
And the next definition is a